Welcome to solverfy.
Okay, in this problem, we're given wavelengths corresponding to the infrared, visible, and ultraviolet range of the electromagnetic spectrum. And we were asked to find the temperature of an ideal black body that would have the peak in its spectral radiation curve corresponding to these values of lambda. So the equation we can use is the empirical equation, which simply states that the peak wavelength multiplied by the temperature is equal to this empirical constant, 2.9 times 10 to the negative 3. So using this equation only, we can find T if we know what lambda is. So it should be relatively straightforward. So let's calculate these. Starting with the infrared. In this case, our temperature would simply be that constant of 2.9 times 10 to the negative 3. This has units of joules meters. So we must divide by a length scale, which will be our lambda. So this is 10 e to the negative 6 meters. So we would have a temperature of 290 degrees Kelvin. So something actually quite cold. Now let's look at the visible range. I imagine it would be something much hotter. So we'd have the same constant, but we're now dividing by 600 nanometers. So 600 e to the negative 9. And we would get a temperature of 4,833 degrees Kelvin. Something much hotter. Lastly, we can take a look at what would be required to be producing radiation primarily in the ultraviolet. Same constant divided by, in this case, our 100 nanometers. Which would give us a very large temperature of 29,000 Kelvin. And that's it. We see that in order to be producing light at increasingly small wavelengths, we need to have something much, much hotter. That's it. Thanks.